Hello and welcome to my today's presentation about truck platooning. My name is Alexander Grazer and I'm working at the Institute of Mechanics and Mechatronics at the TU Wien. The content I'm going to present was elaborated in the context of the Austrian flagship project Connecting Austria. In this project, the impact of energy-efficient semi-automated truck platooning convoys on Austrian roads was investigated. But first, what exactly is a platoon and what are the benefits out of it? A platoon is formed by cars that travel together under reduced vehicle spacing. The main benefits result from this reduced vehicle spacing, namely reduced air drag and therefore reduced fuel consumption and increased road capacity. Sophisticated platoon control also allows safe operation and can help to avoid traffic jams. To realize these small intervehicle distances, collision safety is the most crucial concern and needs to be considered carefully. To harvest the benefits of platooning in the most efficient way, we developed a control concept that can be split up in three main parts. First, the trajectory optimization tool allows a central instance to plan efficient maneuvers. Second, a local model predictive controller is implemented for each vehicle to guarantee collision safety at all times while driving under reduced intervehicle distances. It also utilizes vehicle-to-vehicle communication to increase efficiency even further. Lastly, the developed control concepts were tested in a detailed co-simulation framework for validation. Now let's have a look at the trajectory optimization. We will discuss it on the transition of a traffic light controlled intersection. Here we see a platoon where the positions of the three platoon vehicles and one external follower vehicle are plotted over the vertical time axis. The platoon approaches a traffic light controlled intersection and receives the green light phase via infrastructure to vehicle communication. The platoon coordinator plans the optimal trajectories to pass the intersection without dissolving and without the need of a full stop of the vehicles. Now let's discuss the backbone of our overall control concept, the local model predictive controller that we name SafeMPC. It enables collision safety at all times by considering a worst-case braking maneuver of the predecessor car. Further, it utilizes V2X communication to increase situational awareness and allow efficient adaptation to new traffic situations. One of many features built into the controller is the so-called holdback mode, where the first vehicle basically guarantees to brake less for some time. This results in even tighter platoon spacing and boosts platoon efficiency even further. Now let's look at the Safe by Design concept in a bit more detail. Before we proceed, what actually is model predictive control? In model predictive control, a model is utilized to predict its future behavior over few time steps. The future system response is optimized and then the found control input, in our case the accelerations, are applied at each time step. We can think of this as a trajectory optimization applied at each time step. Why did we choose this control concept? Because it enables optimal control while considering constraints and even incorporating V2X communication. For model predictive control, we need of course a model. Here, for example, we model each platooning vehicle on its own with a state space system of second order, actually a double integrator with the states position and velocity. We discretize this continuous formulation to get a discrete state space formulation that we can use in our control algorithm. We also formulate constraints on the control input, so the accelerations and on the velocities. Then we formulate the tracking problem with a cost function that should be minimized. So actually here we take into account the deviation from a reference trajectory and also the control input, so the acceleration. With the weightings Q, P and R. Next, we formulate our failsafe problem, which actually means that the position trajectory of our vehicle has to be always behind the trajectory of our preceding car at all times. On this picture you can see here the reference trajectory, the actual tracking trajectory, and also in red the failsafe problem trajectory. These two problems are now coupled and yield the overall optimization problem. The goal is to minimize the cost function of the tracking problem, also the cost function of the failsafe problem, and also we incorporate a slack term for feasibility. Now let's look at the tracking problem here. You have the formulation of the tracking problem. It appears in the cost function, and also the regarding constraints on the states and on the inputs are formulated. The same thing is done for the failsafe problem. You can see here also the regarding constraints on the states and the inputs are formulated. And now both of these problems are coupled via the so-called coupling term. You can see here on the left in this picture the dots that are actually the time instants or the sampling points where the two optimization problems are coupled. Of course, if we want to yield efficient platooning with small intervehicle distances, we want to reduce the coupling to a minimum of one sample, which decreases the intervehicle distance to a minimum. By increasing the amount of coupled samples, we can facilitate regularization and therefore disturbance rejection. Now let's have a look at the last main part of our whole architecture, the co-simulation based validation. Here you can see a picture of the co-simulation framework that utilizes MATLAB, Simulink and IPG TruckMaker. In the following you can see a short video we made out of this co-simulation framework. You can see 3 trucks displayed without trailers traveling at closely packed platoon configuration. After some time, the platoon leader receives the message to increase the intervehicle spacing, for example, because of a construction site in front of the platoon. Now let's recap the main aspects of our developed platoon control architecture. We talked about the trajectory optimization tool, which allows to plan efficient platooning maneuvers. Then we covered the safety aspects of the local safe NPCs that are implemented on each platoon vehicle. Afterwards, we addressed our sophisticated co-simulation based validation framework. Here you can see a selection of our publications. An open access book is currently in production. We were able to publish our research in top journals. Our project team you can see here on the left. On the right, there you can see our project partners. We also started a follow-up project recently, which is called Intelligent Intersection. In this project, we want to design an intelligent intersection traffic system for heterogeneous intersection traffic. This should be done by incorporating 5G communication and, of course, improving road and traffic safety. I hope this presentation generated interest in our research topics and maybe also in a collaboration. If so, please do contact us at any time.